Hello and welcome to the seventh video of the operating development lecture series. Today I wanted to talk a little bit about kernel output. So what I really mean by that is how can the kernel give some nothing more that. Now this is very, and I mean extremely useful program. That is because the kernel is gigantic. It spans tens of thousands, if not hundreds of thousands, or millions lines. And imagine writing all of that, not being able to test what this thing in any way. Hence, I wanted to present some extremely simple methods that one could debug using some basic ways that perform output. Furthermore, some of this information will be generally useful if it comes to methodologies in which a kernel can generally communicate with I/O devices. So first, I would like to talk a little bit about actually rendering things graphically, and rendering some text. Fact, a bit about computer graphics and graphical output. The only graphical output that I far is using BIOS to display a character on the correspond to a given ASCII in register during the call. However, video hardware is in reality more sophisticated. So generally have some. Now, one must note that the word screen is a pretty general term. A screen doesn't just describe a monitor. A screen is any sort of peripheral that allows us humans to see things. This means that a projector also screening, and hence can be considered a screen device. So screen, it usually has, well, it pretty much needs to have some interface, some sort of table through which information will be sent. So some of the most notable, slightly older interface, still highly important and had a huge effect on modern graphics, VGA or video graphics. Many of you recognize interface. It was 15 in number one that's later in the port. And another interface that is ubiquitous nowadays, example would be high definition. So you have a screen, it is connected through some cable, some way of sending video data to the screen. So VGA sets a lot of those standards for different things. VGA, it had a lot of modes, and a video mode, certain video mode is in a way okay, you have some data, you have some electric signals. How do you turn those electric signals into something that is actually and the modes themselves, they sort of only define this abstraction, how it's done. It doesn't actually care about how this actually turns all of this data into. This does not matter. What matters is this abstraction of, okay, these are the signals. There's some general specification of how they probably should be displayed and how I should. Fundamentally, a mode, a VGA mode, is pretty much described in timing, right? So these it would be a synchronous in the sense that those electrical signals, they would have to be sent in specific timings according to a given graphical clock or video clock that would, which is it can it would dictate the signals, and according to those timings, the screen can then identify the mode, then use other electrical information, which is actually in the the analog information, which there's a lot of resistors to manipulate that and get it to the correct RGB values, which are stored as analog electrical parameters, and then the screen can understand the mode based on the timings, and then it can adapt and display those analog values in some sort of way so that it is visible. Okay, so now we know that we have to send video data, right, to which fundamentally this video data made out of two primary parts. It needs to send the data according to some timings, video mode. So you need to be sending that data in those timings. This video mode, and then you have the actual pixel. So usually this pixel data through VGA, you then send the data about the individual pixels, which and any other interface. Okay, where do we get this info from, right? Usually, programmer, we don't have to exactly care about the electronic timings. We don't care about the very specific format that one has to actually send the information to the screen. One of those, because this is actually done for us by an extension. So this extension card, video card. So probably seen before, right? It's plugged into one of the buses, like a PC bus, and you know, really, well, pretty much always there are slots, right? There are connectors to those different places that you would connect to a screen. So the term video card has sort of now sort of a thing of the past, and that is because now much have graphics card, right? Now, what is the difference between the two? Well, a graphics is a way more sophisticated. So everything, a video card, what it is responsible for is simply, okay, you have some buffer, you have some data. Let's convert that to electrical signals that will be actually transmitted through one of those interfaces that the screen. So all of that is going to be handled by the video card, but it doesn't do anything more than that. Graphics cards are way more advanced. They have GPU, right, a graphics processing unit, and but they can also do very complicated calculations. So, for example, they can do different matrix multiplications or matrix vector multiplications. And they can generally do things that would be useful in, for example, three-dimensional graphics. So graphics cards are just way more sophisticated, and they have a lot more electronics inside them that are responsible for a variety of different things that are related to actually rendering graphics on the screen. A video card doesn't care about any of that. It assumes that it already has all the graphical data. Everything that it needs to do is manipulate it slightly so that it can be directly sent through one of these interfaces to the screen. So this is everything that the video card is responsible for. Okay, so basically we need to communicate with the video card. So, right, central processing, and we are our kernel is executing its having its executed by the CPU. Okay, so how can the CPU actually communicate with the video card? And this is what I mean by output. We have some way of giving output. How can we actually use the CPU in order to communicate with some video card in order to render to the screen? And sort of the word protocol may be too sophisticated to use here, but I still think we have different methodologies of doing that. I'm going to talk primary ones. I'm going to mention a third one, but I'm going to elaborate on probably. But generally, how do we actually get to communicate? What is the sort of protocol? Fairly accurate. So, the first way that we can communicate with them is actually this approach, and I think it does have its cost. Something called memory map. So, memory mapped I/O. The idea of memory mapped I/O is that you have a region in memory, and it stores something called a buffer. So this buffer, a collection of information that this peripheral device or the extension card sort of continuously, or from every cycle or every couple cycles, it checks this buffer in the memory and treats this as some information in a given format that it. So this is the general idea. Have given regions of memory called buffers that are responsible for storing this information that can be used. So what are some negative sides of the approach? Well, the main shortcoming is that you obviously lose a bunch of memory. I mean, you lose RAM as a could use that for something else. This could be the memory of some program, but instead, this is preserved for some sort of extent. So, especially if you need to store a lot of data, that might not be approach. But that is really not up to us. That's hardware manufacturers. So, let's explore how memory mapped I/O for communication. Now, what I'm going to assume is that the video card is not really a big assumption. Realistically speaking, let me mention, if you have a graphics card, it still has, this sort of, perhaps not video card, but it still has electronics that do the exact same thing. So everything I say for the video card also applies to a graphics card, as it does have. Okay, so pretty much every video card, realistically. So this means even if you're not going to be communicating, like if you're CMI to your, you'll be able to set game mode. So describe how graphics data should, and then you'll be actually use it as if it's game mode, and it will be sent through any of the interfaces so that it can be displayed by the screen. Okay. So the default mode that the video card, the sort of mode that you're in after your computer has used is the 5A. So as the name suggests, mode for rendering text, and we have 80 characters per row, and we have 20. So how do we actually this buffer? It starts at 0x. Well, 0x just starts at address 80. And here you can just place the ASCII of the character that you want to be displayed first position. So this is what we call the base address of the buffer. So we have memory mapped.io. What we have is a buffer. We will have a collection of information in memory that the video card will take and play to the screen. And the base address of this buffer is hexadecimal. And this is where you get to place the first character. So, for example, 65 is the ASCII for capital letter. Most compilers will convert characters to ASCII automatically, because, well, it doesn't really have any other way to store them, coding them realistically ASCII. So you put the value 65 in this address, then it means that you placed 5 in the first address of the buffer. So now, what the video card does is it can either communicate, it depends on the exact technology, but it can communicate with you might communicate, then the CPU might communicate with the memory. There's also this technology called DMA. So DMA stands for direct memory access, RAM, and the video card can access it directly through direct memory access. Might not be the case, depends on the exact technology. Might have to communicate with. So either way, F65 placed at this address, base address of the buffer for this specific mode, but if I recall correctly, for all VGA text modes. I'm not sure about SVGA, because I'm not sure if SVGA surely offers. At least I think so. But SVGA, if you don't know, it stands for Super Graphical, and it was basically an extension before we started generalizing video mode. They decided to also curve. So you place this address, your card reads this buffer and says, hey, okay, we have the value 65. Now, I'm going to turn this whole buffer into electrical signals. The thing is, video card, it will have different, or like the font, and for example, it's ROM, or it might take from a ROM, and you've seen a video card, you know it has a lot of like a ROM. Some of those regions, for example, store fonts. So it says, okay, this is, I know that I'm in a text mode. I know that this is 65, okay, it corresponds to this set of pixels, right? And it's here, so it's here on the screen, so it's going to display the letter. This is the general idea of memory. So you place things into memory, and then it reads from that memory, it reinterprets that way, and then it connects electrical signals, so that will do something. In this example, it will use this send those electrical signals in order to render. And so the screen, for example, if it's a monitor, it will take those values, it will light the red, green, and blue diodes of every pixel according to this, and hence you'll A. Okay, so this is actually even address. The thing about AD text mode is that when you have an odd memory address, it actually doesn't correspond to a character, it actually corresponds to the color of a background, foreground. So the next address, which is decimal B80001, if I were to put another character, which would be, it wouldn't actually give me the capital B. What it would do is it knows how to interpret this buffer. Okay, this is an even address, so I'm going to display the letter A, okay, but I'm going to look at the odd address. What should be the background and the foreground color? Okay, and it's going to interpret this as the background and foreground. It's not going to actually as a character. It's pretty simple to find the document. Leave. I think the first symbol was ground, the second background. It might have been very simple to. And you have you have symbol, right? So you have 16 combinations. You have colors. But the reality is you have 8 colors. 1 bit is for darkening. If it's darker. Very easy to check in with the. You want to mess around with that and have color render. Your priorities, or you're free. So if you were to make a print, then what have to take into consideration is that the next address that would actually render any character would be 0x002. So now if we write 6 to this address, then it will look through the buffer, it will see that it has 65 converted to those pixels. Okay, this corresponds to some foreground and background color, and then it will, okay, the next address, the next even address, like that. Yeah, so if you were to write a print function, you have to remember that you have to actually increment this value by 2. Yeah, so that's the general idea. You're going to make a pointer, and you're going to, using this pointer, you're going to dereference it, you're going to put values inside addresses and value manipulate anything that uses memory. So to provide a more general protocol, check where the base address of a buffer is. You make a pointer to that base address. Then you see what the format is of the information of the buffer and what it corresponds to, the actual peripheral or extension card that you're using. Then you fill those values in the buffer using the reference pointer to the values that you want in order to get that you desire. Then, since peripheral will usually automatically use this information from the RAM, you'll get precisely what you described in the okay, yeah, so that's the idea of memory mapped I/O. Higher video modes are often also memory mapped. Most gay graphics modes, they start at 0x A0. You usually just specify the red, green, blue, and unless it is, for example, a collection of specified a color can be modified. Generally, setting video modes and like statically just sort of set video mode number and then this sort of currently there are more dynamic ways that really check what the screen can do, what your video card, your graphics card can actually render. Based on that, you can get different information and properly render in a video mode. I will probably make a video about rendering graphics. Talk about there. I just wanted to present the general point of how one can use memory.io, and I presented how to use any 80 by 25 character VGA text mode. Then now it is possible to try to print output characters. Obviously, as I said, this takes characters in ASCII, like numbers and stuff. You have to convert those numerical values to characters that represent those numerical values. This shouldn't be difficult. As I pointed out in the lecture, I assume that the viewer has knowledge of computer science and is a programmer. And therefore, I assume that any competent programmer should be able to write such a conversion function without. And if you do, then you might consider rather not sake of first problem. Okay, so this memory map IO. This is the sort of first output protocol and display those values. the sort of other protocol that I wanted to talk about is using I/O bus or data bus. So I have briefly mentioned the idea of in out. Appeared in pseudo assembly, the idea, right? Obviously, for different buses. One of the most important buses is the one that connects you to different points on the motherboard. But okay, it has so many connections, so many different peripherals or extension buses or whatever, other bus manages. So, how does this actually function? How do you know that you're get what you wanted? So the idea is that anything that you would want to communicate with, that's something new. It's and these ports are then connected to over chip or some other program that will know how to interpret. Um, so usually, find is a sort of norm. Not everything follows this norm, but usually there will actually at least two ports for a single device or whatever. And one of them is something called command port. And one is called data port. The idea is that the command port, the one you communicate with in order to give some commands. So like, please give me data about X, or please do this thing. So this is the command port, and then the data port simply contains some sort of information. So you can write to the data port, form something, or for example, it can be a command which requires some parameters, and that you would write to the data ports as well. Or if it's commands to just to give you some data, then in the read of a data port in order to get this. So generally, most assembly languages they offer 6 main instructions managing. Should write a wrapper in whatever language, because I think you're going to write a kernel in a higher level language like that's an assembly. So you write a wrapper around these assemblies if your language is. So first one should be out B. Give it different names. So usually assembly languages out. This is titled out. Sort of the norm to call it out B, which means out byte. So you'll be sending a single byte some port to a bus. This is out B. You can also call it out 8, bits, names you can. kind of out byte. And there's also in B. Going to write B, so it's going to be in byte, so I'm going to read a byte from some port. So this also probably have a wrapper for out W, actually onto out W, in W. So we will output a word, so a 16-bit value, or read a 16-bit value from. Then there's also here the names can differ. Many people just prefer to call it out too, but you can out D, out L, things like that, and that is because what we mean here is outputting a 32-bit value corresponds to out L, long. Something that is long, many people associate it with 60. Actually, not a fully correct association. Programming language is 32. It's a 32-bit value because the reason for this is that back in the day when 32 exists, the numerical type int obviously wasn't 32-bit. So whenever someone would declare an integer, it would be 16 computers. So you declare an integer, and then when 32-bit computers started arriving, people also used integer. Now it was 32-bit, but sort of decided to do this nomenclature. He wanted to short or long. So from now on, the short was a 16-bit value, and a long was a 32-bit value. So this was a really good idea, but because the type int exists and the numerical value, whole number, integer, only 4. So then, since int is for integers, just whenever they belong, you think, okay, it has to be 4-bit value. But it's not the case. A long is 32-bit because back then you had to decide if you wanted short or they wanted long. They wanted 16-bit or 32-bit. And the actual value that corresponds to 64-bit is a long. So that is just so out L is a 32-bit. Remember that was not 60. Some people prefer to call it out D, word, double word, 32-bit. Some people find that less confusing. And in okay, so we need to write wrappers around these functions and then connect. Okay. What could be an example of something? Well, for example, we get the current time using will be CMOS. So CMOS, right? Most people know that CMOS stands for a complementary metal oxide conductor, and basically it refers to an NP entrance, a PNP. What is meant in this context is that this clock is built on top of such pairs. That's why that doesn't matter that much, but basically, you're most likely going overboard a C clock, and one of the being an artist for real time. And it is actually extremely easy to obtain the information out of a kernel time using what I have described here. So, as I said, uh, many devices will follow this command and data port mechanism, and so does the CMOS RTC. So, the command port is decimal. Generally, port numbers are given in hex. So, the command port is actually 70, and is so. You'll always read from the data port. In fact, if you want to make a function, you're going to return whatever you read data port. Could be just value if I remember correctly. Command is also in value. Type of command, it specifies what exactly do. So I will talk about things that three different things that we want to. What is the current second? The current second is given by the command written in binary 1 0 0 0 0. So if you send this to the command port and read from the data port, it will give second. Okay. So we know that this number corresponds to this command. Please give me the current second. And then once we've sent it to bus, what is the current second? Okay. Data port. Now we can read from the data port in order to. Okay. What if we give it a different command? This command. This command, it means please give me the current minute. Okay, so what is the current minute? It gives it to the data port. We can read from the data port, and we will obtain the current binary 1 0 1 0 0. That's hour. But hour where, right? Could be discrepancies. First, no, we have time zones. Well, it's whatever the CMOS RTC is. If you bought the computer in your country, probably be correct. Power losses might have been messed up. You can pretty much always change this in your BIOS. Your BIOS setup, you'll current time. This is what the RTC. So you get to configure. Most virtual machines, that's just they will give you time. Not a huge geography. Yeah, so give it commands, sends both commands, and it gives you back some data. Okay, so again, very simple. And just an example of sort of the time and not really output, but nonetheless, these often are used as an output protocol. Let me give you an example, a very popular example. In fact, this is usually what people do about recursion. And this is to use an interface that, again, most viewers are familiar. RS recommend standard 200, right? Also known as a serial port or just a. So this was used for some peripherals. It was printers, a bunch of for printers. One usually used IEEE 1280 parallel. That's also an output protocol, but it's not that useful nowadays. I mean, the COM port is still sort of still very good for debugging. Most virtual machines will have something called a serial monitor. You'll get real machines might have a serial monitor. They'll display these sort of values sends to the COM port. That is primarily debugging purpose. If you just write to video data, like I presented earlier, you might have issues with scrolling. That is more to implement. Some data might disappear. You can't browse through it or different problems you might encounter. But if you just do a dump send to the serial ports, that can be way more. And there are also operating systems which, by design, they transfer everything to the serial ports, and then they actually what they render is whatever is taken from the serial port. So they have a way to visualize it, and then they dump a lot of things. That is one way that some people actually design their OS. That's pretty interesting. So recommended standard 232 with the COM ports, whatever you want to call it. They are numbered. The only one that I will care about right now. And obviously every port, as I mentioned, in port's number. But we actually know where we're going to data. This one has so it is extremely simple to send debugging data to this COM1. So in order to output something and to be able to then what your kernel does, so your kernel actually has some output protocol, what you can do is simply do an out B to the port 3F7. And you simply send a character there. Simply send an ASCII value, or it can be any value that you want. And if you go to a serial monitor thing, you'll get to that. So it's literally that simple. Many people make a debug print function, just continuously out these different characters that iterate, and what it does is it just sends all those characters through out B 2, 3, 7. Okay. And this is literally how a sort of I/O bus works. So this is everything that I wanted to ask. You know, this mainly was supposed to give this idea of, okay, we're only executing those instructions. How can we actually communicate with all this? I talked about general I/O stuff, but I focused on outputs. So what are those output programs? How can we actually output from our kernel? It should be mentioned that as a design choice, it is often very good for a kernel to, in later stages, you know, not have a lot of outputs that the user directly see. In the sense that You probably shouldn't be rendering your graphical applications, at least not directly, because obviously users will have to communicate with the kernel in order to display those things. But exactly how it is done in all the logic, it should be done by actually executables and not the kernel itself. Okay, so yeah, that is everything, and video I'll be probably talking about interrupt descriptor table, and then I'll elaborate on some I/O use and buses and how more peripheral communication is done and attention. And then our operating system is pretty much going to already comply with one of the points that I mentioned at the beginning. It will manage I/O. At least as in a certain sense. It will manage my system. Which is good because I want to really comply and do what I said in the first lecture. I really want to continue this. I sort of did a list of exactly what I want to do, but I can actually, so that I can finish this, that I have a realistic goal, and I'll actually talk about everything that I want to talk, and then I will finish the series. I talked about everything that I wanted to talk about, so there is pretty satisfying that one can further develop. Okay, and having a realistic vision is very important because, as the viewers, like a lot, really a lot, sort of a personal. So too many. I'm just a person on the internet recording operating system development, like, but this is obvious, but really thinking about it for a second, I have a life, and currently a lot is going on. A lot is happening, and I didn't quite have time to just sit down and actually record a lecture, which is very cool. It's my hobby. It's not even that I don't find the time, but some. Thank you very much for watching this, and I hope that I will see you